What if we could control lightning, bending it through the air like a puppet on a string? Today I'm going to show you a breakthrough that sounds impossible. I'm going to guide electric plasma using ultrasonic waves. Lightning and other electric discharges have a frustrating property. Their motion is seemingly chaotic. It's very hard to predict where a specific bolt of plasma is going to strike next. This is because electric discharges don't just take the shortest path or even the path of least resistance. They take the path that's easiest to ionize. This can create some weird paths. For example, along the surface of glass is easier to ionize than through straight air, so this spark will take the longer path next to the glass slide to shock me, rather than a shorter straight path through the air. Because of this, guiding electric discharges is hard. You have to basically design an easily ionizable path for the spark to follow right before you build up a high voltage. In the past, scientists have tried to make the ionizing paths using high-powered lasers, but the laser can do more damage than the plasma itself, so this isn't really practical in most cases. But there's a new method, one that's surprisingly simple, far safer, and shockingly effective. Instead of using light or radiation, it uses sound. Sound has an interesting property. When it moves between materials with different acoustic impedances, which is a combination of density and sound speed, it can impart a small net force on the boundary between them. This is called the acoustic radiation force. You can see the acoustic radiation force in action when I take two ultrasonic transducers like this. I can create a standing sound wave in between these two transducers. This standing wave will have regions of low pressure fluctuations and high pressure fluctuations, kind of like if I were to shake this slinky and get it to resonate. I'll have regions where there's a lot of movement of the slinky and relatively no movement of the slinky. The places where there's no net movement of particles but high pressure fluctuations are called the antinodes, and the places where there's high movement of particles but no pressure fluctuations are called the nodes. For solid particles larger than a certain size, the acoustic radiation force pushes them into the nodes. Smaller and more compressible particles might be pushed to the antinodes instead, so you can actually levitate particles like this. I made a whole video on this effect alone, which is really cool. But another more interesting effect can also happen with this standing ultrasonic wave. If I have a region of hot air which is lower in density and acoustic impedance than the surrounding air, then the acoustic radiation force will push that hot air toward the antinodes. But what does all this have to do with guiding plasma? Well, remember that plasmas are really hot. Whenever a spark happens, an enormous amount of heat is generated. If I use Schlieren imaging, you can see when I make my Tesla coil spark, I can see the hot air that immediately forms when the plasma goes off. Normally this hot air just mixes chaotically with the room temperature air around it, but not if we have a nice standing wave to put it in. So I have a ring of ultrasonic transducers so that right at the center is a strong antinode. This means that if I have any hot air near the center of the ring, it'll be forced right at that antinode. Now we're getting closer to being able to guide our plasma where we want it. Hot air lowers the breakdown voltage, meaning it's easier for a spark to form than in cold air. You can see if I blow my heat gun between two high voltage electrodes, a spark can form.
It's just the hot air needed.
But if I don't put the hot air there, then it can't form. So if I take a Tesla coil that's pulsing on and off, then the first few pulses will make some hot air, and then after that the hot air will be directed to the center of the rings. Now this creates a path for the next sparks to follow. So what you get is a beautiful guided straight line of plasma coming from the Tesla coil instead of a chaotic mess of sparks. I'm pulsing the Tesla coil's output around 2,000 times per second to create a rapid sequence of sparks that build up hot air. You can see how it makes a nice ordered plasma channel that gives a nice straight line directed wherever I want. Look at that. This is so cool because it has a ton of applications. If you change your ultrasonic transducer location, you can change where the plasma goes. You can even get the spark to go around obstacles. Or you can get it to complete circuits exactly where you want. You can even produce tactile sensations in different spots. This has so many cool applications. It's so amazing that we can actually guide plasma with sound alone. And I want to thank Upna Labs for actually making this ultrasonic ring for me. They've written a great paper on their findings and potential applications. I'll put a link to their paper in the description.